So we will keep going with problems from Halliday, Resnick, and Walker. Um, this time we're going to do chapter 29, problem 1. It's a pretty basic, simple problem for you that is started to study chapter 29 or something like that. Okay. So you can see that my drawings gift skills needs to be improved. So take a look. We have what we have here is a surveyor is using a magnet compass, 6.1 meters. So that means my radius here, the distance is going to be 6.1 meters below a power line. Okay, a power line in which there is a steady current of 100 amperes. So this is going to be 100 amperes. Okay, so the current that is passing here, and I mean it's going to be can be this way. The current can be this way. The current can be this way here. But the important part is the distance, right? And if you're going to affect it or not the compass. Okay. So what we have here is radius and current. Okay, I put here some the constant because maybe we're gonna need it. And the first thing that we can assume here, guys, it's like, look, this really looks like a long wire. So can we use Ampere's law? Yes, definitely. We can use Ampere's law. So because what the question is asking us is what is the magnet field at the side of the compass to the power line. So letter A will be like, okay, so I think I'm gonna use the Ampere's law. So if you remember Ampere's law, it will be a closed path, right? And this closed path here, let me represent, I will try to represent this guy here. So take a look. It will be a closed path. And if you agree, guys, this ds here, this ds can be, for example, I don't know. Let me do this y here, this current here. Okay, so if this going this way, every single ds will be something like this. Okay, so every single ds will be something like this. So this will be my ds. Okay, and because we have the magnet field going, if you use the right hand rule, if your thumb will be pointing this way, your fingers will curl this way here, you're going to see that your magnet field will be at the same direction of the S. So I can choose a right direction here to facilitate my life, right? So we know that this integral here in a closed path, a path that I'm gonna choose. Remember, this is the correlation. This is the Gauss law for magnet field. Okay, so what we have here, it's gonna be mu zero and the current. Okay, so this is Ampere's law, if you remember. Okay, so this is our good friend Ampere's law. Okay, and to use that, well, I created this pathway here. So this is going to be the circle. So what we can do is I know that this field is a steady current. If it is a steady current, will be steady magnet field. So I can send this guy here outside. Okay, so I can put here like vector and so far, but so I have this closed path here, the x, the s, uh, 0, I. So what gonna be this closed path? What gonna be the perimeter? So I know that for a circle, this guy, the limits here, the integration limits will be from 0 to 2 pi r. Agreed? So the integration limits here that for this ds gonna be from 0 to 2 pi r. And because of that, let's now start to calculate the model, I mean the magnitude of this vector here. So the magnitude of b, it will be like 2 pi r, right? Because 0 is not right. It's just the circle here. It's going to be this circle. So it's going to be me 0 I. Okay. So now I just need to put what I need to calculate in one side, and here we're going to have 2 pi r. Okay. Well, we have mu 0, we have r, we have these guys here are constant, current is constant. So let me keep going and calculate my field. So what I have here is going to be 4 pi times 10 minus 7 Tesla meters per ampere, and this will be multiplied 100 amperes. This is going to be my current, and everything going to be divided by 2 pi, and what's going to be the radius? 6.10 meters. Okay, 6.10 meters. So this answer here will be 3.3 times 10 minus 6 Tesla, or I can rewrite this guy as micro Tesla. Well, okay. So far, it's okay because we figure out here what is the magnet field. Cool. Take a look on letter B. Letter B it's like, will this field interfere seriously with the compass reading? The horizontal component of Earth's magnet field at this side is 20 microteslas. Well, if we start to think about that, 3.3 microteslas, it's approximate like 3.3 is approximated 1/6 of the magnitude of the magnitude of the magnitude of Earth magnet field. Okay, so yes, it will interfere. So the answer will be yes, it will interfere. Okay, so this problem, guys, just a reviewing, is a pretty basic. Is the first problem in chapter 29. You need to use Ampere's law. It's going to facilitate your life because you can just create here a closed path with this ds here, simple, okay? And you have everything to calculate. So it's pretty basic. It's easy, this problem. If you need anything else from, I mean, to be honest, you don't need anything else to calculate this guy. Just Ampere's law. Okay, so that's it. Thank you.